Hi, everybody. I'm Jan Wondrak, and this is a talk about the Nash social welfare problem with subadditive valuations. This is a paper with my great co-authors, Shahar Dobzhinsky, Wencheng Li, and Aviat Rubinstein. So let's get to it. This paper is about the following type of problem, a combinatorial allocation problem where we have some items, we have some agents, and each agent has some valuation function which tells you how much the agent values each set of items. And the goal is to allocate the items. So we want to find partitioning into disjoint sets such that agent I gets a set Si, and we would like to optimize some objective. Um, there could be different potential objectives here. Now, broadly speaking, you could consider uh, two notions that we want to care about here, which is number one, welfare. By welfare, we mean allocating the resources efficiently overall, in the sense that the resources should go to agents who care about them in their valuation function. The second general objective is what we call fairness, which is that we want to make every agent happy in some sense. We don't just want to allocate everything to one agent. Now, these two objectives might actually be in some kind of conflict. So this leads to different formalizations of the problem, which leads to different notions of an optimal solution. The first one is maybe the most common classical objective here, which is known as social welfare or Walrasian welfare, which is maximizing simply the summation of the values that the n agents receive. Okay, so that's the classical objective. Now, clearly, this has the downside that if one valuation dominates the others, then the optimal solution might very well be just allocating everything to one agent. And somehow we don't consider that fair. So the second option, which I would say is at the other end of the spectrum, is the max-min objective, also known as Rawlsian welfare in economics, where we only care about how much the least happy agent gets, and we want to maximize that. So that's an option. Now, another notion here is envy freeness, which means that we would like to find an allocation where everybody is happy with what they get relative to what anybody else gets with respect to their own valuation. So these are different objectives. Now, the maximum objective is a little bit extreme in the sense that it doesn't care at all about what the happier agents get. And envy freeness in the combinatorial setting is actually hard to satisfy. So what we will talk about here is another option, another objective, which is known as Nash social welfare. This goes back to a paper in 1950 that John Nash wrote about a certain bargaining problem, where he proposed this objective as the unique objective satisfying a number of axioms. I will not talk about these axioms here, but the objective is simply the product of the values as opposed to the sum, which might look unusual at first, but actually this has a number of nice properties. For one thing, if you scale any of the valuations vi by some factor lambda I, which could be different for each agent, this doesn't change the problem at all. So you could say that each agent is expressing the values in their own currency, and it doesn't matter what the currency is. So that's nice. And because it's a product, naturally this will put more emphasis on the agents which have low value. As I mentioned, there's also the notion of envy freeness, and it turns out that this is actually quite closely related to Nash social welfare in the sense that solutions optimizing Nash social welfare often satisfy some envy freeness properties. I will not have time to talk about this too much, but let me say one more thing about how I view Nash social welfare. I think this is quite an intuitive uh, thing to consider. Suppose that you have some allocation and you are deciding whether there is a way to improve this allocation by swapping an item from one agent to some other agent. So maybe we're doing some kind of local search. When is this actually beneficial in terms of Nash social welfare? Well, it turns out it's all about the relative benefit. Swapping this item J, let's say from agent I to agent K would be beneficial if the new agent derives more relative benefit with respect to what they already have than the relative loss of the agent who had the item. So it's all about relative gain and loss. If you gain 10% from this item and some other agent who had it before loses 5%, then it's a good idea to swap the item. All right, so this actually underlies a lot of the intuition behind some of the algorithms for Nash social welfare. Let me say one more thing just in terms of what we mean by approximation here. We will actually measure approximation factors with respect to the geometric average of the valuations rather than product. This is simply because this is more meaningful in terms of, say, finding factor 2 approximation. This would mean that we lose a factor 2 per agent. Otherwise, if you find a solution where you give everybody 1/2 of what they have in the optimal solution, that would be an approximation factor of 2 to the n. So we just call that factor 2, and that's actually quite reasonable. Okay, so this is the way we measure approximation here. So let's start talking about some classes of valuations, because obviously the difficulty of this problem depends on what the valuations are. Now, the simplest class of valuations here is additive valuations. Let me just remark that the social welfare problem, or Walrasian welfare, is completely trivial with additive valuations. You just give every item to the agent who values it the most. But here, this is already a very interesting non-trivial problem to maximize the geometric average with additive valuations. And this problem actually took quite some time to resolve, in the sense that a constant factor was conjectured but not known. And the first solution was a very nice paper by Cole and Gatsalis in 2015, where they designed a constant factor approximation using a certain market equilibrium approach. An interesting aspect of this problem is that there are several different known approaches, which are really quite different, and they achieve a constant factor in this basic setting of additive valuations. The second approach mentioned here is using a certain relaxation, using stable polynomials. Now, this is related to the maximization of the permanent, also to maximization of determinants. Very interesting approach. It gives a factor of E in this setting. The currently best known factor is E to the 1/E. Now, that's, again, using an approach more related to equilibria in markets, and also a connection with NV freeness. And on the hardness side, it's known that you cannot solve this problem optimally, and it's actually APX hard. So there's a hardness threshold, which is currently something like 1.06. So in that way, the problem is different from social welfare maximization. Now, what can we do beyond additive valuations? We have this popular zoo of valuation functions, which have varying degrees of difficulty. I will not talk about most of them. I will focus on the two most general encapsulating classes here, which are submodular valuations and subadditive valuations. These are quite well known. And this paper is actually about the most general class, subadditive valuations. So before we get to algorithms, let's also clarify how we can actually access these valuations. There are two basic models. Value oracle model, you can only ask what is the value of this set. And demand oracle is a more powerful kind of query where you can set up prices for items, and you can ask what is the most profitable set given prices Pj. So by now, we have quite a bit of understanding of how these classes behave, and the emerging consensus is that somehow the value oracle is the right model for submodular functions, in the sense that you can solve some basic questions with value queries, and you can also solve these more involved problems with value queries. For subadditive functions, value queries are not enough to solve even the basic questions like finding the best set of size k. And the demand oracle seems to be the right mode of access here. So in this paper, we assume the demand oracle model, and we will consider the Nash social welfare problem with demand queries. All right, so here's a table. Here's a table of what is known prior to this paper. Very roughly speaking, there was quite a bit of progress on the Nash social welfare problem recently, which brings the known factors pretty close to what was known for maximization of social welfare, which is generally easier, although we don't have a formal reduction proving that it's always easier, but it seems to be easier. So for example, for submodular valuations in the value oracle model, the factor of E over E minus 1 is known to be optimal in the setting of social welfare maximization. And quite recently, a factor 4 has been found for maximization of Nash social welfare in this setting. So that's not too far off. Clearly, there's a gap in the setting of additive functions because that can be solved optimally in terms of social welfare. And we have a factor of E to the 1 over E, and also APX hardness for Nash social welfare. So the big remaining gap was in the setting of subadditive valuations, and also in the setting of the related class of XOS valuations, which I will actually not talk about here. That's a class sandwiched between submodular and subadditive valuations, and our results will also apply to XOS valuations. So in terms of social welfare maximization, we can get a factor of 2. That was a relatively old result by now by Uri Feige, a really great paper. But not much was known for Nash social welfare. The best factor was actually on the order of n, so linear in the number of agents. And here's our main new result. We achieve a constant factor, which is a large constant at the moment. Let me say 400,000. We could probably improve that, but it's a big constant. So yeah, so how do we do these things? How do we approach the Nash social welfare problem? I mentioned 3 different ways to get a constant factor in the additive setting, and here's actually another one. The most recent approach by Garg, Husic, and Weg is a very nice approach. I would say the most combinatorial out of the different approaches to Nash social welfare. And it's based on the following idea, which is pretty intuitive. If you want to find a good solution for Nash social welfare, then for sure you should give at least something to everybody, because once an agent gets 0, that's bad, and your objective is 0. So why don't we start by giving everybody at least 1 item? And that's actually a sub-problem that we know how to solve well. We know how to find the best solution where everybody gets 1 item, because that's a matching problem. So let's do that first. Well, the only difference is that we are maximizing the product of the values, but that's fine. We can do that by taking logarithms of the values. So let's start by finding this matching. And then they say, well, put the items that participate in the matching on the side and solve the remaining instance somehow. Now, the remaining instance could be a large instance. So let's design some relaxation for it. This relaxation might depend on what particular class of valuations we have to deal with. In the original paper by Garg, Husic, and Weg, they considered a certain class of valuations related to matroids. So there was a natural relaxation for that class. Then they say, let's somehow round this fractional solution. And given the rounded solution, we go back to the items that were allocated at the beginning in the matching, and we possibly rematch them. We find another matching, which is the best possible matching with respect to the allocation that we obtained from the relaxation, okay? Because the original matching might not be the best one with respect to what the relaxation found. Okay, so this is the high-level template. As I mentioned originally, they worked with this template in a relatively constrained setting of valuations which are based on matroids. There's a class called Rado valuations, which I will actually not define exactly here. It combines some features of matroids and matchings. But for this class, they were able to execute this high-level plan in the sense that, number one, there's a natural relaxation here, which is obtained by taking what we call the concave extension. That's denoted here by VI plus. This concave extension can be computed and optimized well in this setting, which can be explained by saying that it's a subclass of gross substitutes valuations. Okay, so this part of the framework works very well. Then they have to do something with the fractional solution. Now, in their setting, that was a relatively complicated part of the paper, which relied on polyhedral properties of matroids, and they achieved a certain sparsification result, which allowed them to say that the rounded solution is very sparse and close in value to the original solution. And then this sparse solution can be combined well with the matching obtained in the last stage. So this was a relatively technical work, very nice paper, which achieved the constant factor for this class of valuations. Now, very quickly, the follow-up history was that this was extended to submodular valuations by replacing the concave extension by the multilinear extension. And this gave some constant factor for submodular valuations. In fact, the factor was not great. It was something like 400, and it was greatly simplified in follow-up work where the factor went down to 4 by eliminating the relaxation completely. So this might be, this is an interesting twist in the story, which seems to suggest that maybe the relaxation is not needed after all, but the matching and rematching is still needed. The matching and rematching was still an essential component of this algorithm for submodular valuations. Okay, but now the class that we want to deal with here is even more general. It's the class of subadditive valuations. And for subadditive valuations, the multilinear relaxation doesn't work very well. We don't know what to do with it. On the other hand, we are now switching to the more powerful model of demand query. So in fact, given that we have demand queries at our disposal, we might as well go back to the initial form of the framework, which considers the concave relaxation. Each valuation is replaced by a concave function. And it's known, it's pretty standard in this area, that with demand queries, you can actually compute and also optimize this concave relaxation. So that's great. We can just go back to this original formulation with concave functions. It's a concave maximization problem. But that doesn't mean that we have solved the problem. The problem, the real problem here is that we don't know how to round the fractional solution. The rounding methods, I didn't really talk about how the rounding worked for submodular valuations, but it's essentially basic independent randomized rounding, which works well for submodular valuations. Here, that's not the case. And the underlying reason is that simple randomized rounding doesn't work well even for social welfare, where we consider the sum of valuations. Now, all this actually goes back to the paper of Uri Feige that I mentioned earlier, which was about subadditive welfare maximization. And that was a very sophisticated paper where he used the configuration LP, very much related to the concave extension that we are considering here. And the question was, how do you round it? The rounding technique was very tricky, very sophisticated, using some kind of item shifting on some big tree labeled with the agents. Very nice paper. I recommend it. The question is, can we somehow harness that here? Because this is actually the only way to get a constant factor, even for social welfare. So what can we do? The method doesn't really seems to work directly for Nash social welfare. But it has a very nice property, which is the following. Now, the relaxation that I'm displaying here is almost exactly what people call the configuration LP, which is the LP from Feige's paper. The only difference here is the log. So there's a log in front of the fractional value that every agent gets. And naturally, the log accounts for the fact that we care about the product of the values rather than the sum. So when you look into Uri's rounding a little bit more carefully, you will see that it actually satisfies a little bit more than just achieving 1/2. Overall, it says that you can find an allocation where at least n/2 agents get at least 1/2 of their LP value. Now, this seems to give only 1/4 overall, right? But we don't care too much about that. The point is that there's an allocation which satisfies many agents as opposed to just giving everything to one agent and deriving the welfare from there. Okay, so many agents actually get something close to their LP value if you look at it carefully. And given that, we can actually do the following. So what I'm describing here is what is happening in the middle layer of the high-level framework, where we deal with the relaxation. We still keep the matching, we still keep the rematching at the end, but we are working with the middle component of this algorithm. So what we do with the fractional solution is based on this observation. Let's say we solve the concave relaxation, then we take the fractional solution and we round it in a way that n/2 agents are happy in the sense that they got something pretty close to what they had in the LP. Fine, so now we can put these agents aside, but we shouldn't use all the items that we have to satisfy these agents. That we would have to stop there. So instead, we only use 1/2 of the items. Basically, we give them a random half of the sets that Feige's algorithm would have given them. And we recurse on the remaining agents. So what happens is that, roughly speaking, n/2 agents get 1/2 of what they wanted. n/4 get 1/4 of what they wanted. n/8 get 1/8 of what they wanted, and so on. So this doesn't look that great, but in fact, in terms of Nash social welfare, this is a constant factor. And that's all based on this infinite product computation, which is that 1/2 to the 1/2 times 1/4 to the 1/4 times 1/8 to the 1/8 and so on, the converging infinite product whose value is 1/4. Okay, so this is a very simplified toy description of our algorithm. There's a lot more going on in terms of making sure that all this works together with the matching and the rematching. But this is the core idea and the underlying reason why we actually get a constant factor. So I think that's the only thing I can explain here. Let me finish again with the table. We found a constant factor, but it's a very bad one. So an obvious question is, can you improve the constant factor? One more version of the problem that I want to mention here is the weighted or asymmetric version of the problem, where you maximize a weighted geometric average. So we have some exponents here, omega I, that sum up to 1, but they could be non-uniform. This is actually a pretty difficult variation on the problem, which was open for a long time, even in the additive setting. There's an exciting new result just now that came up by Feng and Li, which gives a constant factor in this setting for additive valuations. So there's an obvious question whether you can also do that in the submodular or subadditive setting. We don't know if we can do that. All right, so that's it. Thank you very much.